Okay, hello and welcome back everybody. We'll be on to section 1.4, matrix powers, inverses, and the identity matrix. In reality, both inverses and the identity matrix are versions of matrix powers. And so we really are just looking at matrix powers today. So we're trying to analyze this object, some matrix M to the power n. And today we're going to restrict the power n to be an integer. Recall the integers are your numbers like 1, 2, 3, 4, and so on, but also 0 and also -1, -2, and so on. Of course, when we've got -1 there, that's really what we mean by the matrix inverse. So if we manage to define m to the -1 power, that's defining the matrix inverse. Turns out m to the 0 power will be this thing called the identity matrix, the same way something like maybe 9 to the 0 power, or 5 to the 0 power, or -3 to the 0 power are all equal to 1, 1 being our what we call multiplicative identity for the real numbers. And it turns out there are ways of defining matrix powers when n is not in the integers, rather n is any real number, so you can actually have m to the 1/2 power, which would be, some version of the square root of a matrix. Unfortunately, that's not going to be a topic for today. Usually not even a topic in a linear algebra course, often a topic maybe in a differential equations course. It's interesting to think why you would care more about matrices with fractional powers and differential equations than linear algebra, but go ahead and take my course someday if I'm offering it, and you'll see how we do that. But for today, we're just looking at these integer powers, 1, 2, 3, 0, -1, -2, -3. So how are we going to define these? Let's just think about the integer powers of real numbers first. And the way we define those, of course, with the first power, it's just the real number itself. The second power, multiplying the base, right? Recall that 2 is called the base. So we're going to multiply the base the number of times the power exists. So in the case of 2 cubed, we're going to multiply the base 3 times, or 2 to the nth power, we're going to multiply the base n times. If we want to start thinking, as I've mentioned before, 2 to the 0 power happens to be 1, 2 to the -1 power, we start to recover reciprocals. Reciprocals do not make any sense when it comes to matrices anymore. At least we wouldn't want reciprocals in the matrix world, just kind of because of the way they're defined. In a case of like 3, 1, 4, -2, if I want to invert this, I actually really do not want this to be equal to 1/3, 1, 1/4, and -1/2. Turns out that this right-hand side object of just computing the reciprocal of every term doesn't really have any useful properties. We really want to define the inverse in a way, I'll mention this now, we want to define this in a way that it properly encapsulates the quote-unquote opposite of matrix multiplication. And of course, because matrix multiplication has this very interesting row column interactions where you're multiplying each entry in a row against each entry in the column, then adding all those terms together. If you're going to try to do the opposite of that, right, the inverse of that, you're going to come up with different operations than just 1 divided by something, because that's when we multiply matrices, we're not just performing an element-wise multiplication. So naturally, we're going to define the positive powers of a matrix to just be the matrix multiplied by itself that many times. So MQ would be m times m times m, but we should just keep in mind this is interpreted as matrix multiplication, the way that we've already been studying matrix multiplication. Okay, so positive power is really not too bad to define. Let's look at an example of some matrix powers to positive integers. Here I have the matrix 1, 2, 0, -1. If I want to take that matrix to the first power, it's just going to be itself. So it's 1, 2, 0, -1. If I want to take it to the second power, this is where things finally get interesting. I'm just going to multiply the matrix by itself. So I'll have 1, 2, 0, -1 times 1, 2, 0, -1. And then let's recall how we actually compute matrix multiplication. I'm looking at rows on the left and I'm looking at columns on the right. And then I'm going to compute the first entry in the first row, first entry in the first column, second entry in the first row, second entry in the first column, and add all of those together so that the top left ends up being 1. I can also do the first entry in the first row by the first entry in the second column, the second entry in the first row by the second entry in the second column, so that my top right ends up becoming 0. I can then take the first entry in the third row, the first entry in the first column, and then the second entry in the third row, second entry in the first column to get 0, the bottom left, and finally the first entry in the second row and the first entry in the second column, plus the second entry in the second row and the second entry in the second column to recover a 1. That ends up being the second power of this matrix. If I wanted to look at the third power of the matrix, I'm just going to do this again, multiplying the matrix 3 times. Now, we can cheat a little bit, and it's not really cheating, but we can just play the game. This is called associativity, right? By associativity, we can use our previous result to make the computation easier, in the sense that, well, I already computed this, right? I've already computed m squared. That's the matrix by itself. So if I group those terms together, I already know what their answer should be. Their answer is exactly 1, 0, 0, 1 that I've already computed. So I can save myself a little bit of time, and I'm actually in the third matrix power computing m against the second matrix power. Right? Okay, so now we're just going to compute m against the second matrix power. First row on the first column gives me 1 times 1 plus 2 times 0. There it is. So that's going to give me a 1 in the top left. Then I have a 1 times 0 plus 2 times 1. That's right here. That's going to give me a 2 in the top right. Then I have a 0 times 1 plus negative 1 times 0. That's going to end up giving me a 0 in the bottom left. And finally, I'll have a 0 times 0 plus negative 1 times 1 in the bottom right. That's going to give me a negative 1 in the bottom right. And so we see our third matrix power as the matrix 1, 2, 0, negative 1. It's fairly straightforward for those positive powers, but now we should start talking about maybe the power 0 or some negatives. And of course, naturally, in the real numbers, anything to the 0 power is defined to be equal to 1, and anything to the negative 1 power, you start with the reciprocal, and then if I start taking higher orders of negative powers, we really think of 2 to the negative 2 power as 2 to the negative 1 power squared, and at that point, since we've already defined 2 to the negative 1, and we've also happened to define squaring, we're just going to get 2 copies of 2 to the negative 1 power multiplied together. And we'll do the same thing with negative cubes or negative nth powers. And so all our job will be, in terms of matrices, is to define this 0 power and this negative 1 power, and then everything else below should come for free. So the 0 and the negative 1 are the important ones for us. So how should we define the 0 power as some version of some matrix version of 1, right? We want the 0 power to serve the role of 1, but inside of the matrix world. You may think that the answer to that would be the matrix 1, 1, 1, 1. Definitely feels like a matrix version of 1. It turns out that's not as good of a definition. And this is maybe not great because we would want some notion of, if I take a matrix and maybe I multiply it by this matrix of all 1s, I would want that to leave, the original matrix unchanged. We want the 1 to leave m unchanged from multiplication. But if we actually go through that procedure, in the event that we have a 1, 1, 1, and a 1, if I go ahead and multiply a matrix, let's say 1, 2, 0, negative 1, by the matrix of all 1s, 1, 1, 1, 1, and I run my matrix multiplication with my rows on the left and my columns on the right, what do I actually end up getting? Well, I'm going to take 1 times 1 plus 2 times 1. I'm going to get a 3 in the top left. Then, of course, as I continue, I'll have a 1 times a 1 and a 2 times a 1. I'll end up with a 3 in the top right. You'll get a 0 times a 1 and a negative 1 times a 1. You'll get a negative 1 in the bottom left, and then a 0 times a 1 and a negative 1 times a 1. You'll get a negative 1 in the bottom right. And of course, this matrix we just constructed, 3, 3, negative 1, is very much not equal to the matrix we started with. And so this notion of all 1s, matrix of all 1s, just won't be the right choice here. So what should the right choice actually be? Well, it turns out we have a definition for the right choice. The definition, and the name we give this matrix, is called the identity matrix. Identity is a mathematical term that means leaves something unchanged. Okay, so in this case, it's leaving other matrices unchanged when you multiply by it. So it's called the identity matrix, and it's defined as 1s along the diagonal. So you get 1s along the, and really this is the top left, bottom right. Every time we say diagonal in matrix world, we're talking about this top left, bottom right diagonal. So obviously there's the other diagonal, the bottom left, top right diagonal. We don't refer to that as the diagonal. It's always top left to bottom right. So 1's along the diagonal and 0's everywhere else. So this matrix, no matter what the size is, right, it's always going to be n by n. It'll be square. But aside from that, no matter what the size of this matrix is, if you go ahead and multiply by it, it's going to leave the other side of the multiplication unchanged. Now, I want to mention there's multiple ways of denoting the identity matrix here. I've used what's called the blackboard bold 1. So it's got 2 strokes in the center of a 1, but obviously there's an ID, short for identity, or sometimes people will just use a capital I to denote the identity matrix. So a few different notations there. I'll go with the fancy 1 in this course, just because it really does behave like a multiplicative 1. It's got a couple examples of the identity matrix. So in 2 dimensions, we of course have the 2-dimensional matrix with 1's along the diagonal and 0's along the other spaces. If we perform the matrix multiplication against 1, 2, 0, negative 1, we're going to put rows on the left, we're going to put columns on the right, and we're going to perform a multiplication. That's going to give us 1 times 1 plus 0 times 0, which is of course 1. It's going to give us 1 times 2 plus 0 times negative 1, which is of course 2. It's going to give 0 times 1 plus 1 times 0, which is 0. And it's going to give 0 times 2 plus 1 times negative 1, which is negative 1. Similarly, if I decided to act this identity matrix on the right instead of on the left, right, even though we're swapping now, right, rows have become the left-hand matrix and columns are on the right-hand matrix, this is still going to work out as the identity for us. We're going to get 1 times 1 plus 2 times 0, which is just going to give me a 1. We're going to go 1 times 0 plus 2 times 1, which is still going to give me a 2. We're going to get a 0 times 1 plus negative 1 times 0, which is still going to give me a 0. And we're going to get 0 times 0 plus negative 1 times 1, which is still going to give me a negative 1. And so no matter which side this identity matrix is acting on, it's still going to provide the overall identity computation. The output's always going to remain unchanged. Let's go through one of these 3x3 identity cases as well. Maybe we'll choose the bottom case. This is where I'm multiplying on the right by the 3x3 identity, right? We're still seeing 1's along the diagonal and 0's everywhere else. And let's go ahead and perform the multiplication. We're looking at rows on the left, columns on the right. And so I'm going to compute 1 times 1 plus 2 times 0 plus 3 times 0. And you can start to see how this works, right? The only piece that survives here is the first one, 1 times 1. So we get a 1 in the top left. Same thing is going to happen once I multiply by the middle column, right? I'll have a 1 times 0, but then the 2 times 1, the middle term will remain, and then a 3 times 0. So we'll get a 2 in the middle column. And then if I look at the right column, 1 times 0, 2 times 0, 3 times 1, the only term that remains is the 3 times 1. If I repeat with the middle row, I have a 0 times 1, negative 1 times 0, negative 2 times 0. The only term that remains is really the 0. 0 times 1 is the one that remains. And then I have middle row, middle column, 0 times 0, plus negative 1 times 1, plus negative 2 times 0. The only term that remains is the negative 1 in the middle. My middle row against my last column, 0 times 0, negative 1 times 0, negative 2 times 1. And the only term that's going to remain is the negative 2 times the 1 at the end. Then my bottom row against my left column, negative 3 times 1, 1 times 0, 0 times 0. The only term that's going to remain is the negative 3. Then bottom row, middle column, negative 3 times 0, 1 times 1, and 0 times 0. Only a 1 will remain. And then finally, negative 3 times 0, 1 times 0, and 0 times 1. Nothing really remains, but you could think about it as a 0 that remains, and we get exactly the matrix that we started with. So these serve as the identity matrices, and once we have a notion of an identity matrix, right, we can actually start to think about what m to the 0 would mean, right? Because we're going to send the 0 power to the multiplicative identity, whatever that happens to mean. Okay, so we actually have a proposition, rather than you just looking at some examples, there is a proposition that states, yes, this has to be true, no matter which matrix I put on either side of the identity, I will always remain where I started. The proof is quite intense, right, because we have to follow the true definition of matrix multiplication, so the proof takes a little while. Okay, so now we've officially defined what M0 is, M0 being this identity matrix, and we earlier defined all of M1, M2, and M3. We just need to decide what these negatives will be, and in fact, right, from my discussion earlier, we really just need the first negative power. And so how are we going to come up with this? We're going to come up with this. There's really two answers to how we can come up with it. The first is one that maybe I should have actually taken in this text, but the first answer is that recall that m represents a linear function. You can let m inverse be the matrix representation of the inverse function. Okay, this is a perfectly true definition that we could work with, and it does happen to be equivalent to the definition we're going to choose instead. So you could just say, hey, we're going to find an inverse function, and then we're going to ask for the matrix representation of that. But the other answer is what I've provided below, is that we just require that m inverse matrix multiplied by m, which of course is m to the first power, you just get to add exponents the same way you would add exponents with real numbers. So if I add -1 to 1, I get 0, and we've already identified that the 0 power has to be the identity matrix. And so it's just going to be defined as whatever matrix I have to provide next to the original, so that if I multiply the two of them, I end up at the identity. And that is, of course, if you understand how matrix representations work, the exact same operation as the one that requires m inverse to be the matrix representation of the inverse function. So, these are equivalent definitions, but the one I've provided below is maybe a little bit more straightforward in terms of how are we going to compute these, right? I think, thinking about the matrix inverse as this object computationally will make our lives a little easier. So what we're going to do is we're just going to require that, powers of matrices add together, and then the matrix inverse is exactly whatever matrix is required to give us the identity matrix out of multiplication. So how would I actually find something like that? Let's say I have a matrix here, 1, -1, -2, 1, and I want to find its inverse. Let's say I want to find some other m, so that when I multiply it, okay, I want to multiply by m inverse, and I want to recover the identity. Remember, the identity, at least in 2 dimensions, will be 1, 0, 0, 1. What should this matrix actually be? Well, the easiest way to find that matrix is to just give it some variables. I like going with A, B, C, and D as my variables for this unknown inverse matrix. And then I'm just going to directly compute the multiplication with the matrix I wish to invert. And then I'm going to perform the multiplication on the left. So when I perform the multiplication on the left, what do I actually get? Well, as always, I'm looking at rows on the left and columns on the right. It's going to end up being 1 times A plus -1 times C. So A minus C, for example, on the top left, I'm going to have 1 times B plus -1 times D, or B minus D in the top right. I'm going to have -2 times A plus 1 times C, or -2A plus C in the bottom left. And I'm going to have -2 times B plus 1 times D, or -2B plus D in the bottom right. And so that's what happens if I actually perform the left-hand side multiplication. I'm just going to keep the right-hand side the same. So that's why I have a 1, 0, 0, 1 on the right-hand side there. But what have I come up with by actually performing this multiplication? Each entry on each side must agree, right? There's an equal sign there. Because of this equal sign, every entry on every side must agree with the entry on the other side. So A minus C has to be equal to 1. B minus D has to be equal to 0. -2A plus C has to be equal to 0. -2B plus D has to be equal to 1. The moment I have that equality, that each entry has to be true, we can just reduce to a system of 4 equations with 4 unknowns. Of course, the unknowns being A, B, C, and D, and then we're going to solve, in this case, for A, B, C, and D. So if I look at my system of equations, how would I want to solve these? Well, looking at this center row, B minus D is 0, that's pretty easy to solve for either B or D. You find out really quickly B and D are in fact the same object. And once you know B and D are the same object, you look at this bottom row, you know that B and D are the same, so -2B plus D is actually -2D plus D is -1, or in other words, -D is 1, or D is -1. So you find out D is -1 quite quickly, but on top of that you find out B, which happens to be D, is also -1. So we found B and D. Now we're going to have to analyze the A and the C rows. The second row there, -2A plus C is equal to 0, can be rearranged to tell me that C is actually 2A. And once I know C is actually 2A, I can go ahead and substitute that into the top row by replacing C with 2A. If I replace C with 2A, I get A minus 2A is 1, or in other words, -A is 1, or in other words, A is -1. Once I know A is -1 and I know C is 2A, that tells me that C is -2. Okay, so there I found D is -1, B was -1, C was -2, and A was -1. We have A -1, B -1, C -2, D -1. So we've gone ahead and found our inverse matrix just by setting up a system of 4 equations and solving all 4 equations. So now that we know that we can potentially find inverse matrices, we can go ahead and define all matrix powers. So the matrix power, m to the n, is just going to be defined as n copies of the matrix, so long as n is positive. It's going to be defined as n copies of the inverse matrix when n is negative, and of course it's going to be defined to just be equal to the identity when n is 0. So that's going to be all matrix powers for us. And these matrix powers have very natural properties, right? They do indeed satisfy that you can add the powers together when you're multiplying them independently, or even if we want to take multiple powers, m to the n to the m, we can just go ahead and multiply the powers together. So everything you would expect from matrix powers holds. Let's talk about why we even wanted to define these in the first case. Now, it turns out the ones that are important to define are the ones that we spent the most amount of time on today, the identity matrix and the inverse matrix. But of course, there are other reasons you may want higher powers of other matrices, maybe just not today. We might see them eventually. But the identity and the inverse are going to be quite important. And in fact, the inverse is especially important because inverse matrices are going to help us solve systems of linear equations. And so this is a proposition for now. We'll go through some examples very quickly. Let's just look at a generic, very large system. All right, this is a generic, arbitrarily large system of n equations in n unknowns. Now it's very important that the number of equations, the number of unknowns are the same. This is actually what allows us to have a square matrix here. This will end up being a square matrix. You can of course convert the system of equations into a matrix dot vector product, and then you just say this is equal to a vector, where the vector on the right now is the vector of these coefficients, b. So we've written out the system of equations now as matrix times vector equals vector, or equivalently, in maybe the nicest notation you've seen so far, matrix times vector equals vector. This is really why linear algebra is important, because we can convert that giant system of equations, which is super ugly to write, just down into the kind of the single equation, mx equals b, at which point it's quite easy, as long as m inverse exists, right? It's quite easy to know that we can just compute m inverse on both sides, and because of the properties of the inverse matrix, when the inverse multiplies the regular matrix, those two cancel, and we just end up with x, the solution, right? This is the solution, because that's what we've been looking for the whole time. The solution is equal to m inverse times b. And so the fact that you can write, or really solve any system of equations as m inverse times b, matrix inverses make your life quite easy. Now, you need to know the inverse exists, and you need to find the inverse. So in those cases, things can be a little tricky, but aside from that, it's quite efficient to solve systems of equations. So let's go ahead and at least include some very quick ways of computing the inverse, at least in 2 dimensions. So in 2 dimensions, we can quite efficiently compute the inverse matrix using the following formula. It's going to be 1 divided by AD minus BC. So that's when my entries are A, B, C, and D. We get 1 over AD minus BC. And then what do? We swap A and D, and we make B and C negative. So we swap A and D, and we make B and C negative. Now this front term, 1 over AD minus BC, you probably just want to go ahead and memorize that term. So you memorize 1 over AD minus BC, you memorize that you swap A and D, you memorize that you make B and C negative. And once you remember those 3 items, you can invert any 2x2 matrix quite quickly. We have a proof here that this actually does compute the inverse. You go directly with the proof. You just go ahead and make an actual matrix multiplication. You find out you get 1, 0, 0, 1, which is the definition of the inverse. But what we actually care about is quickly solving systems of 2 equations rather quickly, rather efficiently, using matrix inversion. So here I have a system of 2 equations. I've got x plus y is 2, I've got x minus 2y is 3, and I would like to find the solution as quickly as possible. Well, the nice thing about matrices is I can just look at these coefficients. I have 1, 1, 1, negative 2, and I basically put those coefficients in a matrix. I put my 2 and my 3 on the right-hand side in a vector, and we just send ourselves to the matrix vector equation. 1, 1, 1, negative 2, acting on the vector xy is equal to the vector 2, 3. And so all I need to do to compute the answer, and I've got a little typo here, I need an inverse there. All I need to do is take the inverse matrix of 1, 1, 1, negative 2 and pull it to the right-hand side, right? So I'm going to get 1, 1, 1, negative 2 inverse acting on 2, 3 on the right-hand side. But now I will have to actually compute this inverse, and we're going to use our formula, right? The formula for a 2x2 inverse is 1 over AD minus BC I'm going to swap A and D, so that's going to be D, A. I'm going to make B and C negative. So that's what I'm using here. We're going to identify A, B, C, and D. We're going to go ahead and compute 1 divided by A, which is 1, D, which is negative 2, minus B, which is 1, C, which is 1. And then we're going to swap A and D around. So if D was negative 2, that ends up in the top left. If A was 1, that ends up in the bottom right. And then I'm going to make B and C negative. C was 1, so that becomes negative 1. B was 1, so that becomes negative 1. Now I'm just going to simplify this. And to simplify it, we find out that we have really negative 1/3 is what my 1 divided by AD minus BC becomes. And that negative 1/3, we're just going to go ahead and grab it and distribute it to each of the terms inside the matrix. We can say that our new matrix, or our inverse matrix, is 2/3, 1/3, 1/3, negative 1/3, which means up here, still have the typo, but up here, that inverse, we're just going to go ahead and replace the inverse with 2/3, 1/3, 1/3, negative 1/3. And then we're going to perform the matrix multiplication, 2/3, 1/3, 1/3, negative 1/3, on the vector 2, 3. And we're going to end up with, well, we look at rows and columns, right? Rows and columns. We're going to take 2/3 times 2 plus 1/3 times 3. That gives us 7/3. We're going to take 1/3 times 2, negative 1/3 times 3, and that gives us negative 1/3. So we find out that xy, the solution to the system, happens to be, well, x, the first entry, x is 7/3, y, the second entry, is negative 1/3. And so you immediately can find the solution to the system of equations just using matrix inverses. I've got one more example here where in reality I'm never going to make you find like a 5x5 matrix inverse. I would only ever do actually a 2x2, even 3x3 and above. I'll just like have a computer find the inverse anyway, because computers are pretty good about finding these inverses. There's some good algorithms that people have developed for finding inverses. So in this case, I'm just providing the inverse of this giant 5x5 matrix that we see here. And it turns out this inverse is what's on the right-hand side. It's got a lot of these 1/5 sitting through there. But that's going to serve as the inverse of the 5x5 matrix I provided on the left. And I'm saying, provided that we have the inverse, I can efficiently solve a system of 5 linear equations rather than going through a bunch of substitution methods. I can efficiently find the solution by, well, what are my coefficients here? Let's give ourselves an ordering, x, y, z, u, v. Then we have the coefficients 1, well, we're missing y and z, so plus 0y plus 0z, minus 1 plus 1 equals 1, right? So what are the coefficients here? 1, 0, 0, negative 1, 1. There you go, 1, 0, 0, negative 1, 1, and so on. You'll have to trust me that the coefficients of all these lines actually align with what I've provided inside of our matrix here. And so we do have the matrix representation of the left-hand side given by this matrix, and then our right-hand side is really the vector 1, 1, 1, 2, 1. So I put all this in a big old vector, some squiggly brackets there. Put all those into a vector, and how do we find our solution? Well, we write it as the entire system as a matrix vector equals vector equation. All you have to do to pull that matrix to the right is put an inverse on it. And once the matrix on the right has an inverse on it, well, we know what the inverse is because somebody was nice to us and provided it. We're going to go ahead and act that inverse matrix on the vector of coefficients that we want our system to be equal to. Now, when we do this, we should directly replace the inverse with its actual computation, which is here with all the 1/5, and then we get to go through the work of taking every row on the left-hand side and multiplying it by the column vector. On the right-hand side, what do we have? We have 1/5 times 1 plus 0 times 1 plus 4/5 times 1 plus 2/5 times 2 plus 1/5 times 1. You just go ahead, grab a calculator, plug those in, you end up getting a 2. You can then do the second row, 1/5 times 1, 0 times 1, negative 1/5 times 1, 2/5 times 2, 1/5 times 1. Add all those together, you end up with a 1. Third row, negative 1/5 times 1, 1 times 1, 1/5 times 1, negative 2/5 times 2, 4/5 times 1. Add all of those together, you end up with a 1. And then you take the fourth row, negative 2/5 times 1, 0 times 1, 2/5 times 1, 1/5 times 2, negative 2/5 times 1. Add all of those together, you get a 0. And then finally the last row, 2/5 times 1, 0 times 1, negative 2/5 times 1, negative 1/5 times 2, negative 3/5 times 1. Add all of those together, you end up with negative 1. Therefore, if you look at the solution, right, we're just comparing x, y, z, u, v with the vector we just produced, 2, 1, 1, 0, negative 1. We find out that x is 2, y is 1, z is 1, u is 0, and v is -1 as the solution to the original system. Final example shows one example of another use of matrix power. So this is not going to rely on the inverse or the identity. It actually relies on the second power of a matrix. And this is pretty cool. This example shows the double angle formula from trigonometry. And so what are the double angle formulas from trigonometry? Let's go ahead and jump all the way down to the end, and then we can see what the actual proof looks like. The double angle formulas are given here on the bottom. They say that cosine of 2 theta is cosine squared theta minus sine squared theta, and then they also say sine of 2 theta is 2 cosine sine. Those are the double angle formulas, so-called double angle, because you start with 2 multiples of the angle, you end up with just a single multiple of the angle theta. So how could we prove it? Well, you can prove it directly using trigonometry. That maybe would have happened if you've taken a course in trigonometry, but matrix powers allow us to prove this more directly. So let's think about the following function. We've got this multidimensional function f sub theta. And this function is going to map two-dimensional space to two-dimensional space. We're going to define it by taking the input x and the input y and outputting cosine theta. That's where that subscript theta is coming in. So there's some parameter theta here that this function depends on. But you just choose some theta before you use it. Well, it takes cosine of theta and it multiplies the x input, and then it subtracts sine of theta multiplying the y input. That's going to be the overall first output. And then it's going to take sine of theta times the x input, and it's going to add cosine of theta times the y input. And that's going to be the overall second output. Now this might seem like a somewhat strange function to actually introduce. What does this function do? It's defined to rotate a point, the input point. It's going to rotate it counterclockwise around the origin by an angle of theta radians, of course. So for example, if I decide to stick theta at pi over 4, we're calling it pi over 4 is equivalent to a rotation of 45 degrees, we can write out explicitly what f of pi over 4 would look like. It would look like, well, because cosine and sine of pi over 4 are 1 over root 2, it would look like all of these cosines and sines here all become 1 over root 2. We have 4 different 1 over root 2's hanging out. You end up with x over root 2 minus y over root 2 as your first output, and x over root 2 plus y over root 2 as your second output. And if you don't believe me, that is actually rotated by 45 degrees. I've gone through and computed the outputs of 1, 0. That happens to be 1 over root 2, 1 over root 2. The output of 1, 1 becomes 0 root 2, and the output of -2, -2 becomes 2 root 2, 0. And if we actually plot the input and the output on a single plane, you can see, yes, the input 1, 0 rotates counterclockwise 45 degrees to 1 over root 2, 1 over root 2. The input 1, 1 rotates counterclockwise 45 degrees to the output 0 root 2, and then the input -2, 2 rotates 45 degrees counterclockwise to -2 root 2 and 0. I do see I'm missing a negative sign up here. Anyway, so that's going to be the case of pi over 4, but we do want to keep this actually in this special case of just theta, right? So we're going to say all the way at the very top here, if I just give myself any theta here, I've got cosine, negative sine, sine, and cosine. We can construct, this is a linear function, and so a matrix representation exists. In fact, what is it in this case? We call it r theta, r for rotation. The matrix representation, we're just looking at the coefficients, right? The coefficients of the first output, cosine and negative sine. So we have cosine theta, negative sine theta, and then the coefficients of the second output, sine theta, cosine theta. Okay, so we've got this matrix that we can use to represent our function. It's a 2 by 2 matrix because the function maps two-dimensional space to two-dimensional space. It's cosine theta, negative sine theta, sine theta, cosine theta. Let's go ahead and compute the second power of this matrix, meaning we're going to take the matrix and multiply it by itself and perform a matrix multiplication. We're looking at rows here and columns here. And I'm not going to go through all of the work of the rows on the columns, but I will talk about directly, if you just compute and simplify, the outputs will be cosine squared minus sine squared in the top left. You'll get -2 cosine times sine in the top right. You'll get 2 cosine times sine in the bottom left. And you'll get cosine squared minus sine squared in the bottom right. Now this is the action of rotating by theta twice, right? Because r theta by itself rotates by theta, but of course if I multiply it by itself, I'm just doing it again. So r of theta squared represents the action of rotating by theta twice. But let's also think about what maybe r of 2 theta would be. This, which by the way is right, it's cosine of 2 theta, negative sine of 2 theta, sine of 2 theta, and cosine of 2 theta. This is going to represent the action of rotating by an amount 2 theta. Of course, rotating by theta twice and rotating by 2 theta should be the exact same thing. I mean, these angles add together. If I'm just doing something twice and things add together, then I'm just doing it 2 times. So 2 times theta is theta twice, right? But what that means is that this matrix that I've just computed using matrix powers and this matrix, which I've just computed directly, have to be equal. These two matrices have to be equal. Well, that's only going to be the case if their entries are equal. What is the top left entry? It's cosine squared theta minus sine squared theta, but the top left entry is cosine of 2 theta. And so we find out that those two terms are equal. Or we could look at the bottom left entry, 2 cosine theta sine theta and sine 2 theta. Those two entries have to be equal. And those are exactly the double angle formulas from trigonometry. Anyway, we're going to stop there. There's kind of a cool application right at the end that I like quite a bit. Get excited for the next one. We're going to talk about determinants, eigenvalues, and eigenvectors. I'll see you then. Bye.